This is our second lecture on hypothesis testing. We performed a couple of problems in the first lecture using that z-test, hypothesis test number 1. Mu is known, sigma is known. We're trying to answer a research question. Is there a significant difference between the population mean and the sample mean? That's the real general question. Let's get a little bit more specific. Problem number 3. Currently, the usable life of a computer chip is 16,000 hours. With a standard deviation of 2,500 hours. A microprocessor company has developed a new fabrication process which they believe will increase the usable life of a chip. They manufacture 1,000 chips and plan to test their microprocessor against the current market norm. Class, what is the current market norm? Yeah, it's 16,000. Mu is the norm. Mu is the norm. They discovered that the usable life of their chip is 16,500 hours. We have a research question. Does their new chip have a significantly greater usable life than the norm? I don't know. Beats the heck out of me. What I do know is we have about a 500-point difference between mu and x bar. Yeah. I mean, there is a difference. What we want to know, is there a significant difference between the sample mean and the population mean? And it has everything to do with what's going on over here on the sampling distribution of the mean, this underlying sampling distribution as put forth in the central limit theorem, right? Where does this individual sample mean fall on the sampling distribution? Class, little review. If this sample mean falls right here, it's going to correspond to a z a little bit less than 1. What's our decision going to be based on the null?
Accept the null.
Accept the null. This should come now immediately. Okay, we've had Friday, Saturday, Sunday. We've had 4 days since the last class. That's 4 days of practice. 4 days of practice. This stuff should be coming immediately. You're going to be tested on it. Class, if this sample mean, on the other hand, falls right about here,
Reject.
our decision is going to be to reject. So everything in the middle is the non-rejection region. Everything in the tails is the rejection region. We have our first set of information. We have a population mean of 16,000. This is the norm. Our job is to determine where does that sample mean fall. We have this z-test that's going to help us make that determination. Z is the sampling error numerator divided by the standard error of the mean. And we know the standard error of the mean, sigma over the square root of n. We know the standard error of the mean is just simply the standard deviation of all those infinite amount of means around mu. We write the null hypothesis, h sub 0 colon mu equals 16,000. The alternative hypothesis, h sub 1, mu is not equal to 16,000. We only run two-tailed tests in this class. This is a classic two-tailed null and alternative scenario. Equal sign, not equal sign. No difference, there is a difference. This thing calls for an O1 alpha and a two-tailed test. And again, our researcher chose a two-tailed test because before they gathered these 1,000 chips, they didn't know whether this sample mean would be above the population mean or below it. Turned out to be above it, that's fine, but they didn't know that at the outset. Picked a two-tailed test just to be safe. The truth is, the two-tailed test is much more scientifically credible. I'll explain that to you a little bit later. we know that before we run any statistical test, p equals alpha. It's going to change. And because we have alpha of 0.1 and a two-tailed test, what are our z-critical values, class?
2.58.
Positive or negative 2.58. And it is crucial that we know why this is so. If you go to your z-tables, you will see, if you go to the z258, you will see 0.0049 area from here back and 0.0049 area from here back. And if you multiply 0.0049 by 2, two-tailed test, right, you get what? 0.01. 0.01 something, but 0.01 for all practical purposes. Half of the P region lies this way. The other half of the P region lies this way. We're running a two-tailed test. Step number 2. And we have a population mean of 16,000. Let's run the z-test and see what's going on. Z equals 16,500 minus 16,000 over our standard error of the mean. The standard error of the mean is going to tell us a lot. We kind of back into this thing in terms of, this is going to give us a real good idea of what's actually going on. Sigma, 2,500, over the square root of our sample size, 1,000. That's 2,500. Square root of 1,000 is 31.62. Standard error of the mean, in this case, is 79.06. 79.06 hours. That's our scale of measurement. So we know that one z unit in this case equals 79.06 hours. Let's do what we do over here. 16,000 plus 7906, 16,079.06. And then let's do this again. What is this? $16,158.12, and then let's do it one more time. What's that?
16,158.12.
Okay, and then add 79.06 to that.
So 16237.18.
Very good. We have enough information now to make a pretty decent determination. Now, all we have to do, where does this individual sample mean, 16,500, fall on the sampling distribution? Oh man, it's like way out here. See that? What's our decision going to be based on the null? We're going to reject. And now we're just going to formally run the z-test just to confirm that. 500 divided by 79.06 gives us a z of 6.32. And we will now formally use the rule, which is the critical value approach in the book, right? We compare our calculated test statistic to the critical value. We see that it exceeds it, in this case the positive direction, therefore our decision is to reject the null. Reject the null, yeah. Let's answer the question. Class, does their new chip have a significantly greater usable life than the norm? Yes. Yeah. So whenever we reject the null, that answer is going to be yes. Whenever we accept the null, it's going to be no. Yes, we have a statistically significant difference in this case. So something happened to P as a result of this needle shift from positive 258 over to 632. What happened to P, everybody? Yeah, it got smaller. If P is less than alpha, we reject the null. But what really happened here? Well, let's look at it. The needles started right here and here at the critical values. But Z turned into 6.32. This area remained at 0.0049. But this needle shifted from 2.58 all the way over to 6.32. This area of P got really, 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 really small. I'm saying really, 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 really small. Like, you know, so small that it's not even in our charts. This Z is so large that it's not even in the tables. I mean, I'm talking this area, 0.000000000000000000. It's pretty small, isn't it? Yeah. Is P less than alpha? Yeah. You know, is P less than 0.1? Yeah. If P is less than alpha, reject the null. If P is greater than alpha, if Z would have been, if that mean would have fallen right here, and Z would have been positive 0.8, the needle would have shifted back this way and made this area of P larger. If P is greater than alpha, what's our decision? Accept the null. Very good. This is, again, class, like every good boy does fine. Okay? If you're a musician, you want to become a good musician, you practice. And a lot of times that practice involves doing your scales. Okay? Practicing your scales. This is like these are all the basics. This is the stuff that you just have to rep. You got to go through this. And it's important to know what's happening. Where does the sample mean fall? Well, in this case, based on the information, that 16,500 is way over here. It corresponds to a Z of 6.32. Pretty doggone rare events, right? Rare events are significant events. In fact, this Z is so rare that it's been deemed a significant event. We have a statistically significant difference between the population mean and the sample mean that in this case falls way over here. Now, there is a small likelihood that my decision to reject the null was not a correct one. So I rejected with about 99% certainty, about a 1% chance that, you know, my decision is not a correct one. And of course, the likelihood I committed a type 2 error is irrelevant. That becomes a non-issue. I rejected this statement, thereby accepting this statement, which states that the population mean is something different than 16,000. It actually might be, I'm not saying it is, but it may be 16,500. We may have what we call a paradigm shift. Okay. The Z-test. Answering the question, is there a significant difference between the population mean and the sample mean? Let's try this again. We'll go on to the next problem. Here's a problem out of education. The national average reading level for high school sophomores is 150 words per minute. We have this national average. That's a lot of data. It's a lot of data. The national average reading level for high school sophomores, they have that information. It's 150 words per minute with the standard deviation of 15. So they had this big data set, and they summed all the reading scores, divide by the number scores to get the mean. Then they used the computational formula for variance. They computed a variance of 225, right? Then took the square root of 225 and got 15. A local school board member wants to know if sophomore students at Lincoln High School read at a level different from the national average for 10th graders. A random sample of 100 10th graders were drawn, and the resulting average was 157 words per minute. Again, this first set of information should look familiar to you. If you didn't do any of this homework, not a good idea. I wasn't getting any responses. Research question. Do Lincoln's 10th graders read at a significantly higher level than the national average? I don't know. What I do know is that we have a 7-point difference here. You know, the question becomes, where does this individual sample mean fall on the sampling distribution? I don't know right now. It could fall somewhere in the middle. What would my decision be if that was the case? Except, if it were to fall out in the tails, what would my decision be? Very good. So our next step, we set the null and the alternative. On the exam, you will have some stuff just like this to work on. I'm going to ask you questions, one of which is write the null and the alternative. So what you do, if you want to get it right, you say h sub 0 colon, in this case, mu equals 150. Look in chapter 9. Chapter 9 is very big in this section. Look at the two-tailed test and how they do things. Alternative hypothesis, h sub 1 colon mu is not equal to 150. This thing calls for an O5 alpha and a two-tailed test. And again, our researcher chose a two-tailed test because before they gathered these 100 subjects, they didn't know whether the sample mean would be above the population mean or below it. They picked a two-tailed test just to be safe. We know that before we run any statistical test, p equals alpha. It's going to change. Right now, p equals alpha. And so, because of that, our z-critical values are positive and negative 1.96. And we know why that is so, right? We all know why that's so. If we don't, there's a problem. We've had 4 days now. Your expertise should be increasing. The critical values are here and here. 2.5% area this way. We're running a two-tailed test. 2.5% area this way. If you add those two areas together, you get 5%. The p region is cut in half. We're running a two-tailed test. Half of p is this way, half of p is this way. 2.5% area this way, 2.5% area this way. Add them together, we get 5%. There's a reason why I'm repeating this and repeating this and repeating this. Because you need to know it, okay? We have phase 2. We have a population mean of 150. That's the norm. Let's run the z-test, see what's going on. We're going to take a look at that standard error of the mean. 157 minus 150 divided by the standard error of the mean. Sigma 15 divided by the square root of 100. That's 15 over 10. Standard error of the mean is 1.5. So the standard deviation of that sampling distribution is 1.5. But we don't call it standard deviation. We call it the standard error of the mean. It's actually a form of sigma or S. So class, tell me, quiz question, test question. In this case, what is one z unit equal to? 1.5, yeah. Let's do our thing. 150 plus 1.5, 151.5, 153, right? 154.5. We could actually do it on the minus side, but we know some things now, don't we? See that 157 over there? Where does it fall on the sampling distribution?
Way left.
Do you see what's going on? It's very important that you do to understand this visually. 157, here's 154.5, so 157 is like way over here somewhere. What do you think our decision is going to be in terms of the null? Question, do we have a significant difference between mu and x bar?
Yes.
Are you getting it? Good. And you have to get all the little pieces and parts. What's actually happening? The needle actually shifted on this side. This area of P stayed at 2.5%. This area of P got way smaller. It shifted from 196 over to whatever Z was. What was Z? I can't see it over there.
Z is going to be
Oh, we didn't compute it yet. Let's compute it. 7 divided by 1.5 equals what?
4.67.
Positive 4.67. Okay, now let's formally make the decision using the rule, using that critical value approach in the book. We compare the calculated statistic to the critical value. We see it exceeds it, therefore our decision would be to reject the null. Yeah, if a calculated test statistic exceeds the critical value, there's another test question, by the way. In fact, this exam coming up a week from Thursday, what's it going to be on? What do you have to know? Everything. Yeah, everything. Yeah, you need to know everything. So whatever I've talked about in class, there's a reason for it. Because it's really important. It's what you need to know. So I'm going to test you on everything. All the pieces and parts, right? And how they work together. Now we're working on how they work together. So we rejected the null. So immediately we know what happened to the P region. Yep, it got smaller. Yep, if P is less than alpha, we reject the null. This area remained at 2.5%, but this needle shifted from 196 over to 4.67. It made this area of P way, way smaller. Again, this side of P is a number really, 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 really small. It results in a P value really, 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 really small. Do Lincoln's 10th graders read at a significantly higher level than the national average?
Yes.
Yeah, apparently so. We have statistical evidence that suggests that Lincoln's 10th graders may very well read at a significantly higher level than the norm. Now, I'm not saying that I'm proving anything. I'm not proving that Lincoln's 10th graders read at a higher level. I'm providing statistical evidence that suggests, the wording is really important. I'm providing statistical evidence that suggests that this sample of Lincoln 10th graders may very well read at a significantly higher level than the norm. I'm not proving anything. I'm just providing statistical evidence to support or not support a particular statement. I've rejected this statement, thereby accepting this statement, which states that the population mean may very well not be 150. It may be something else. It may, I'm not saying it is. It may be 157. What I really want you to get here is this idea of this statistically significant difference between mu and x bar, which in this case is 157. This distance is large enough to be deemed significantly different. Why do we have significance? Because z is 4.67. It's right over here. Stuff that happens in the tails are rare events. Rare events are significant events. Again, think of a rare event in your life. Graduating from high school, graduating from college, having your first child, getting your driver's license. All are pretty rare events. They're significant events that don't happen every day. Getting married. Rare events are significant events. Let's do this again. Data gathered from all 50 United States over the past 10 years revealed that the national average on the Stanford happiness scale, a measure designed to determine overall personal happiness and fulfillment with life, was 38 with a standard deviation of 12. Again, a big population data set on happiness. A random sample of 49 individuals from Port St. Lucie, Florida. Wow. Was administered the Stanford happiness scale, and their mean was 43. Are the subjects who live in Port St. Lucie significantly happier and more fulfilled than the national average? Again, I don't know. What I can observe at this point is we have about a 5-point difference between mu and x bar. But what we really want to know is, where does this x bar fall on the sampling distribution? If it falls out in one of the tails, it's going to correspond to a z that's larger than one of our critical values in most cases. If it falls somewhere in the middle, it's going to correspond to a z that's less than, so to speak, the absolute value of our critical values. Regardless, we have our first set of information with a mu of 38. That's the norm. We're going to see if this sample of 49 individuals is significantly happier than the norm. We write the null and alternative, h sub 0, colon, in this case, mu equals 38, h sub 1, colon, mu is not equal to 38. Again, we have a classic two-tailed null and alternative scenario. Equal sign, not equal sign, look in chapter 9. This thing calls for an O1 alpha. So we have a stricter alpha here. It's going to take a higher test statistic to reject, and we're running a two-tailed test. And again, our researcher chose a two-tailed test because before they gathered this data, they didn't know whether the sample mean would be above the population mean or below it. Turned out to be above it. That's fine. They picked a two-tailed test just to be safe. We know that before we run any statistical test, our p region equals alpha. And we know, because alpha is O1 and we're running a two-tailed test, that our z critical values are positive and negative 2.58. And of course, we know that because we're getting real good with these areas now, aren't we? Yeah, we're getting real good with these. It's becoming second nature now. We know that about 0.5% falls from this position back, and about 0.5% falls to the right of positive 2.58. And if this confuses you, look at your z tables. We have our second set of information. And it'd probably be a good idea to compute this z with a special emphasis on that standard error of the mean. It's going to tell us a lot in terms of where the individual sample mean falls. X bar 43 minus mu 38 divided by the standard error of the mean, sigma 12 over the square root of 49. That's 12 over 7. In this case, one z unit is going to equal 1.71. One z unit is 1.71. The standard error of the mean, in this case, based on the information, 1.71. What this is saying is that the standard deviation of all these individual, sample means around mu is 1.71. We don't call it the standard deviation. We call it the standard error of the mean. We'll go out in units of 1.71. 38 plus 1.71, 39.71. Somebody help me?
41.42.
41.42.
43.13.
Very good. Things get a little clearer now, don't they? Yeah. You should all be looking over here and comparing the sample mean where it falls on here. Where does that 43 fall? Well, yeah, absolutely. In fact, the 43, I bet you this sample mean is about right here. It's going to correspond to a z a little bit less than 3, about right here. Just off the top of our heads now, because we're getting pretty smart now, what do you think our decision is going to be based on the null?
Reject the null.
Yeah, because it goes through this critical value. It's now, rare enough to be deemed a significant event. Well, let's compute z and make the formal decision. 43 minus 38 divided by 1.71 gives us a z of positive 2.92. Yeah, we were right, a little bit less than 3. Let's make the decision formally. We'll compare the calculated test statistic to the critical value. We see it exceeds it in the positive direction. Therefore, our decision based on this null is to reject the null. Yeah. And just, real quickly, what happened to our p region, everyone?
It's less than.
Yeah, it actually got smaller. And let's examine that. This particular example, it's kind of easy now. Look, the needles started at the critical values. Positive and negative 258. Z turned into 2.92. This area from here back remained at 0.0049. But this needle shifted from positive 258 to positive 2.92, thus making this area of P smaller. Class, go on your new Z table, go to a Z of 2.92, tell me that area beyond Z. Tell me that proportion greater than Z. What is that number?
0.0018.
0.0018. The P region is actually 0.0067. Is 0.67% less than 1%?
Yes.
Yeah. Is 0.67% less than 1%? Yes. If P is less than alpha, reject the null. So the P region was reduced from the area was reduced from 1% down to 0.67%. If P is less than alpha, we reject the null. The whole purpose of this is to answer a question. Well, now we have enough evidence to be able to do so. Let's do that. Class, are the research subjects who live in PSL significantly happier and more fulfilled than the national average? Yeah. You know what? There's something about, the water they've been drinking here in PSL, or, the sunshine, or whatever. Okay? There's something special about this particular sample. That this particular mean is a rarity. It's a pretty rare event. This is the norm. This is everyday average stuff. This is not. This is something really special. Now again, there's about a 1% chance that my decision to reject the null was not a correct one. So I rejected with about 99% certainty. The likelihood I committed a type 2 error is a non-issue. Again, let's drill a little bit. Z was 2.92. Class, if Z would have been 1.36, what would my decision have been? Accept the null. If Z would have been negative 0.75, what would my decision have been? Accept the null. Yeah. If Z would have been negative 1.53, what would my decision have been? Right. If Z would have been negative 3.68, what would my decision have been? Reject the null. Very good. Very good. Reject, accept. Our goal is to reject. That's what we're looking for. Sometimes we're able to accomplish it. Other times we're not. Coincidentally, in these beginning examples, we've been rejecting. That's not going to be the case. We're going to spend the whole semester on different types of hypothesis tests. We're going to do a lot of accepting as well. Just so happens coincidentally that we've been doing a lot of rejecting. Now, I said that the likelihood I committed a type 1 error is 1%. I basically said I rejected with really high certainty. There's another interpretation for this. They actually go over it in chapter 9. Another way of interpreting this alpha is that if I were to replicate this 100 more times, I would correctly reject the null 99 times and incorrectly reject the null 1 time. Let me repeat that. Another interpretation for this alpha is that if I were to replicate this scenario in terms of repetitive sampling, in other words, if I were to take 100 more samples of 49, therefore computing 100 more means, I would correctly reject the null 99 times and incorrectly reject the null 1 time. The probability of a type 1 error. Okay. On your syllabus, for chapter 9 are a series of problems. I would like you to practice those problems. We're going to conclude this lecture, and I have a few more comments to make before I dismiss you. Thank you very much.